In a chemical reaction, chemical equilibrium is the state in which both reactants and products are present in concentrations that have no further tendency to change with time, so that there is no observable change in the properties of the system. In a simpler explanation, we can say that it is a condition in the course of a reversible chemical reaction in which no net change in the amounts of reagents and products occurs. A reversible chemical reaction is one in which the products, as soon as they form, react to produce the original reagents.
In the next example, we can see how is the chemical equilibrium in a reaction. When we put reactives that are N2 nitrogen plus H2 hydrogen, the reaction produces 2NH3 ammonia. But the reaction is too fast that the product comes back to be the two elements separates, and it is represented by a symbol that are two arrows with different direction. For this, we need certain conditions for obtain a reversible reaction.
Constant of equilibrium is a number that expresses the relationship between the amounts of products and reactants present in an equilibrium and a reversible chemical reaction. For can calculate its constant, consider the following reversible balanced reaction. A plus B react into C plus D. If we know the molar concentrations of each of the reactions species, we can find the value of the constant using the relationship, where C and D are the concentration of the products in equilibrium, A and B equilibrium concentration of reagents, and A, B, C, and D are the stoichiometric coefficients of the balanced equation. Some important data for the constant are that the constant is the result of a reaction in a determinate temperature. If the temperature changes, the constant will change. The constant is rated without units in the majority of the case. The reaction must be balanced with the coefficients written as the minimum integral value possible in order to obtain the correct value. If the constant is of 1000 or more, the product have more equilibrium in the reaction. If the constant is 0.001 or minus, the reactive have more equilibrium. And finally, if the constant is between 0.001 to 1000, the reaction have an equality equilibrium. In the next example, we explain how to calculate the constant of equilibrium if we have the molar mass of each reactive and product. Let's look at the equilibrium reaction that occurs between sulfur dioxide and oxygen to produce sulfur trioxide. The reaction is in equilibrium at a certain temperature. The following equilibrium concentration being measured: sulfur dioxide 0.9 mol, oxygen 0.35 mol, and sulfur trioxide 1.1 mol. We can calculate with the next expression, and then we put the value in moles for each one of the products. The result is that the constant is equal to 4.3. It considers that since the calculated value of the constant is between 0.001 and 1000, we will expect this reaction to have significant concentration of both reactants and products in equilibrium, as opposed to having mailing products or mailing reactants. And with this example, we can understand how to calculate the constant of equilibrium. Now we can pass to the next topic.
Henry Louis Le Chatelier was born on October 80 of 1850 in Paris, France. He died on September 17 of 1936. He was a French chemist who is best known for Le Chatelier's principle. Le Chatelier's principle is an observation about chemical equilibria of reaction. It states that change in the temperature, pressure, volume or concentration of a system will result in predictable and opposing changes in the system in order to achieve a new equilibrium state. Le Chatelier's principle can be used in practice to understand reaction conditions that will favor increased product formation.
Change in concentration. According to Le Chatelier principle, adding additional reactants to a system will shift the equilibrium to the right, towards the side of the products. By the same logic, reducing the concentration of any product would also shift equilibrium to the right. The converse is also true. If we add additional product to a system, the equilibrium will shift to the left in order to produce more reactants. Or, if we remove reactants from the system, equilibrium will also be shifted to the left. For example, in the reaction between sulfur dioxide and oxygen to produce sulfur trioxide.
Change in pressure. Change in pressure or volume will result in an attempt to restore equilibrium by creating more or less moles of gas. For example, if the pressure in a system increases or the volume decreases, the equilibrium will shift to favor the side of the reaction that involves fewer moles of gas. Similarly, if the volume of a system increases or the pressure decreases, the production of additional moles of gas will be favored. Lastly, for a gas pulse reaction in which the number of moles of gas on both sides of the equation are equal, the system will be affected by change in pressure.
Change in temperature. The effect of a temperature on equilibrium has to do with the head of reaction. Recall that for an endothermic reaction, heat is absorbed in the reaction and the value of delta H is positive. Thus, for an endothermic reaction, we can picture heat as being a reactant. If we raise the temperature on an endothermic reaction, it is essentially like adding more reactant to the system, and therefore, by Le Chatelier's principle, the equilibrium will shift to the right. Conversely, lowering the temperature on an endothermic reaction will shift the equilibrium to the left, since lowering the temperature in this case is equivalent to remove a reactant. For an exothermic reaction, heat is a product. Therefore, increasing the temperature will shift the equilibrium to the left, while decreasing the temperature will shift the equilibrium to the right.
Addition of catalyst. In a equilibrium reaction, the addition of a catalyst increases the forward and reverse speed in the same proportion. As a consequence, the balance is not affected. If the reaction has not reached equilibrium, the addition of the catalyst will cause it to be reached in a shorter time. But at the end in the process, the quantities of products and reagents will be the same as they would have been if the catalyst had not been added. In conclusion, Chatterley principle, according to which in a equilibrium system an external pressure, temperature or concentration factor is modified, the equilibrium shifts in a way that compensates for alteration produced. Chatterley worked in specific colors of gases at high temperatures, and optical chronometer was invented to measure temperatures beyond the limits of mercury thermometers. He promoted the application of chemistry in French industry, and the research affects products such as ammonia and cement. He also worked on steel and ceramic.